This is section 7.3, complex numbers in polar form. Here are the objectives. What we want to do here is basically we're going to plot complex numbers and write them in different forms. We will also find products and quotients, multiple powers, and nth roots. The first thing we will address is plotting complex numbers in the complex plane. So I want to remind you that a complex number is a plus bi, where there are two parts. A is the real part and b is the imaginary part. And there are two axes that are required to represent this. We will have a real axis, which is the horizontal axis, and the imaginary axis, which is the vertical axis. The real and the imaginary axes together produce the complex plane. So if I were to plot some complex numbers, the one in red here, 2 plus 3i, has a real part of 2, so we will go to the right 2. It has an imaginary part 3, so we will go up 3. So this is very similar to the ordered pair 2, 3. Similarly, this complex number is very similar to the ordered pair -1, -2, because the real part is -1, the imaginary part is -2, and we would plot that in the third axis. I'm sorry, the third quadrant. So let's go ahead and plot some of these. In number 1, we have the complex number -1, -5i. This is very similar to this ordered pair, but the real axis is here, the imaginary axis is here. If I were to plot this, I would go left 1 and down 5 units, which is here. So this is -1 minus 5i. 3i is only the imaginary part, so it's right on the imaginary axis. If I wanted a similar ordered pair in rectangular form, it would look like this. So this is 3i. -4 is on the real axis, so it would look like this. Now I'm going to just add one in here for the heck of it. Let's say we want to graph 2 minus 3i. This would be the ordered pair 2, -3. So we would go right 2 and down 3 here. So 2 minus 3i. That's really all I'm going to show you regarding plotting the points because I feel it's pretty straightforward. So a little bit more to talk about is the distance between our values. So the distance between the origin and this ordered pair. That distance is found by taking the square root of a squared plus b squared. And that is called the modulus, sometimes referred to as the magnitude as well. So if you're asked to find the modulus, it's represented by the absolute value of z, and you would take the square root of a squared plus b squared. So here are some examples. If you want to find the modulus, it's represented in this way. This is a, this is b. So to find it, we will take the square root of -7 squared plus -12 squared. When we square root or take the square of each of those, we will get 193. So the modulus is root 193 here. Same thing here. This is a and b. So the modulus is found by taking the square root of 4 squared plus -6 squared. Remember, we can't take the square root of these terms individually because we are adding them. So we end up with the square root of 52. If you want to reduce this, you can. The largest perfect square that goes into 52 evenly is 4. 4 times 13 is 52, and this reduces to 2 root 13 for the modulus. Okay, so here again we have this complex number, and it's said to be in rectangular form because of these ordered pairs. So we're just going to kind of analyze this a little bit. So the information on this slide is stuff that we have seen before. It's really nothing new, so you can pause this if you want. But basically, we know that A is equal to r cosine of theta, and B is equal to r sine of theta, very similar to x and y. And so in this case, we can rewrite here. So this z equals a plus bi, so this number can be rewritten by replacing a and b here, and then factoring out the r. As we know, there are lots of choices for theta, but typically in radians, we will choose a value of theta between 0 and 2 pi, and 0 and 360 for degrees. A little bit more to talk about before we get into the meat of this. Writing the polar form of a complex number. So sometimes, in the previous slide we saw this, but sometimes we shorten it and we say r cis theta, and all that means is cosine I sine. So this, and this. So we're kind of lazy, and so sometimes we say that. So for example, we can write it out like this, but we can use a little bit of shorthand to say 2 cis pi over 3. So these two things are exactly the same. There are a couple other examples here that you can take a look at as well. Okay, so here's what all of this information means. We have this complex number given to us where this is A and this is B, and we want to write it in polar form. So if we want to write this in polar form, we need to find r and theta. Okay, so in order to do that, let's analyze this a little bit. If I were to plot this complex number, it would be in quadrant 3, which is helpful to know, all right? Now, from previous knowledge, we know that we can find r by taking the square root of a squared plus this, b squared. Okay, so if I evaluate this, I end up with 1. Okay, so we have found r. Excellent. Now we need to find theta. Well, we know that tangent of theta is y over x. So that's negative root 2 over 2 divided by negative root 2 over 2, which is 1. So tangent of theta is equal to 1. This occurs at some multiple of pi over 4. And since we are dealing with quadrant 3, we are here, and the multiple of pi over 4 in quadrant 3 is 5 pi over 4. So instead of using this form, I can rewrite this in polar form by using this formula, r times cosine of theta plus I sine of theta. So z is equal to, in this case, r is 1, so we don't need to write it, but we will have cosine of 5 pi over 4 plus I sine of 5 pi over 4. If you evaluate this, it will get you right back to where we started. So it's nice to have that as a check. Let's try another one. Okay, so we want to write this complex number in polar form. Okay, so if I were to plot this, I would see that this is in the first quadrant because both A and B are positive. You can also think of this as X and Y if you want. So I know that R is found by taking the square root of 12 squared plus 5 squared. This gives me the square root of 169, which is 13. Boom, I have R. Now I need to find theta. Tangent of theta is y over x, which is 5 over 12. Now 5 over 12 is not on our unit circle, so I will take tan inverse of both sides. So theta is equal to tan inverse of 5/12. This is approximately 0.39 radians. Well, I have R and I have theta, so I can go ahead and write this in polar form. Remember, if I need to write something in polar form, I need R and theta, which I have. So this is equal to 13 times cosine of, if I want to write it exact, it would be like this, plus I sine of tan inverse of 5/12. And remember that this just represents some angle, and we have found it. You can rewrite it as 0.39. In fact, you can also say R cis 0.39. Okay, so this, remember, is our modulus, and this is our argument. Here's another example. Now, this is written in polar form because we have R cis theta, and we want to rewrite it in rectangular form. So we want it to look like this. Okay, well, this is quite easy because all we need to do is evaluate this and evaluate this. I know that 135 degrees is here, and this makes my reference angle 45 degrees. So here we have z equals 6 times, in quadrant 2, the associated ordered pair with 45 degrees is negative root 2 over 2 and positive root 2 over 2. So cosine of 135 degrees is negative root 2 over 2 plus sine of 135 is positive root 2 over 2 times I. Now, to get this into rectangular form, I will distribute that 6 and reduce. So this becomes negative 3 root 2 plus positive 3 root 2 I. And that is the final answer. Sometimes we will want to find products and quotients of polar numbers of complex numbers in polar form. And when we do that, we have some formulas, and just looking at this, it seems a little intimidating, but here's all this is saying. This is saying we have one complex number in polar form, and we have another complex number in polar form. If I want to find the product, if I want to multiply those, I will use this formula. I'll multiply the r's, add the thetas. On the other hand, if I want to find the quotient, or if I want to divide these complex numbers that are written in polar form, I will divide the r's and subtract the thetas. Let's try it. Okay, so as promised, I have two complex numbers, 1, 2, and they're both written in polar form. We want to find the product. So in order to find z1 times z2, we will multiply the r's and we will add the thetas. So we will end up with cosine of 30 degrees plus 210 degrees plus I sine of 30 degrees plus 210 degrees. Then, of course, we will add those and multiply this. So we get 60 times cosine of 240 degrees plus I sine of 240 degrees. And really, that's all there is to it. There is no need to move further because it says to write our product in polar form. I have an r and a theta. This is polar form. If I'm asked to write this in rectangular form, which I'm not, but if I'm asked to write this in rectangular form, I will evaluate this, and distribute the 60, and I'm done. Okay, let's try this one. Same thing. I have two complex numbers in polar form, and I want to find the product. So z1 and z2 become 3 times 2 times cosine of, we're going to add the thetas and multiply the r's. So pi over 12 plus pi over 6. All right, at this point you should be an expert at adding fractions with unlike denominators. This can be written as 2 pi over 12. So if I were to add these, I would have pi over 12 plus 2 pi over 12, which gives me 3 pi over 12. 3 pi over 12 can be reduced to pi over 4. Okay, so this is equal to 6 cis pi over 4. I took the shorthand notation on that one. Okay, in this example now we're going to find a quotient, and this is the only one in which we'll find the quotient, but it's very similar to the others. So if I want to find z1 divided by z2, I will divide the r's, so 8 divided by 2 times, then I will subtract the thetas. So it will be 7 pi over 12 minus pi over 4 in each of these arguments. Okay, again, you are an expert now at adding and subtracting fractions with unlike denominators. So this can be written with a denominator of 12. So I have 7 pi over 12 minus 3 pi over 12. This is equal to 4 pi over 12, which reduces to pi over 3. So all of this equals 2 goes into 8 4 times, and I have cis pi over 3. There you have it. Okay, so now we are looking at something similar but different. So I need to take a different approach. Now notice that these complex numbers are written in rectangular form. They're not written in polar form. So if I want to find this product and write it in polar form, the first thing I need to do is rewrite Z1 and Z2 in polar form. So I'm going to rewrite these in polar form. So let's start with Z1. Z1 I know is in quadrant 1 because both values are positive. That's helpful to know. So R is equal to the square root of 1/2 squared plus root 3 over 2 squared, and this becomes 1. Then tangent of theta is equal to, in this case, the square root of 3 divided by 2 divided by 1/2. This is root 3. In quadrant 1, this means that theta is pi over 3. I have R and I have theta, so Z1 can be written in polar form as R cis theta. I'm going to do the exact same thing with Z2. I have to rewrite these in polar form because the formula to find the product of Z1 and Z2 requires that these numbers are in polar form. So Z2 is also in quadrant 1. So same type of thing. You will find that R is equal to 1. I'm going to wave my hands a little bit. And tangent of theta ends up being root 3 over 3. So in quadrant 1, theta is pi over 6. So Z2 in polar form is 1 cis pi over 6. Okay, so now that we have our two complex numbers in polar form, on the next slide I will go ahead and find the product of those. So recall that Z1 is cis pi over 3 and Z2 is cis pi over 6. So remember, when we find the product Z1 and Z2, we multiply the R's and we add the thetas. You should be able to add that and find that we end up with cis pi over 2 for the final answer. Believe it or not, sometimes we will want to compute powers of complex numbers. And in order to do this, we use a little something called de Moivre's theorem. Now, some people pronounce this in a different way, which I believe to be the incorrect way. So this is de Moivre's theorem. And basically, again, it is saying if we have this complex number, then if we raise that to a power, it is found here. So we will take R to the power of n and theta times n. So let's see how this works. Now, one thing I want to point out is that the complex number is written in polar form. Okay, so here we have a complex number written in polar form. The catch in this problem is that we want our result to be written in rectangular form, which shouldn't be that difficult if you know how to use your unit circle. So let's go ahead and see how this works. Okay, well, I want to raise this complex number to a power of 4. So what I'm going to do is the following. This will be equal to 2 to the power of 4 times, now what I'm going to do is multiply the argument by 4. So I'll have cosine of 4 times 3 pi over 16 plus I sine of 4 times 3 pi over 16. So I need to simplify this and reduce it. 4 goes into 4 once and into 16 4 times. So don't forget to raise 2 to the power of 4, giving us 16 times cosine of 3 pi over 4 plus I sine of 3 pi over 4. Now, if we were asked to write our result in polar form, we would be done. But because we're asked to write our answer in rectangular form, we need to take this one step further. And it's not too terrible because all I need to do is evaluate cosine of 3 pi over 4 and sine of 3 pi over 4. Now, 3 pi over 4 is in quadrant 2, and the associated ordered pair of pi over 4 in quadrant 2 is negative root 2 over 2, root 2 over 2. So I know cosine and I know sine. So this becomes 16 times negative root 2 over 2 plus root 2 over 2 times I. Once I distribute this 16, my rectangular form becomes negative 8 root 2 plus 8 root 2 times I. And that is the final answer. Let's try another one. Now, this one is different because our complex number is written in rectangular form. I cannot use de Moivre's theorem until this is written in polar form. So the first thing I need to do is write this in polar form. So to write it in polar form, I need r and I need theta. So remember, r is equal to the square root of 2 root 3 squared plus 2 squared. This becomes the square root of 16, or 4 in this case. So we know r. Tangent of theta in this case is 2 divided by 2 root 3, which becomes root 3 over 3. Tangent of theta equals root 3 over 3 when theta is equal to pi over 6. Okay, so we know that in rectangular form, we have 2 root 3 plus 2i to the 6th. This is equivalent to 4 cis pi over 6 in polar form, raised to the power of 4. Applying de Moivre's theorem, this is equal to 4 to the 4th. I'm sorry, 6th. I don't know where the 4 came from. Sorry, 6. Times cis 6 times pi over 6. 4 to the 6th is a big number. It is, I believe, 4,096. The 6's cancel, so cis pi. This is the result in polar form, but we want rectangular form. So you need to evaluate cosine of pi and sine of pi, which is -1 and 0 respectively. So this becomes 496 times -1 plus 0i. 0i goes away, so this result in rectangular form is -4096. Okay, well, sometimes we want to find powers of complex numbers, and we also want to find nth roots of complex numbers. So here's what I mean. Again, if I have a complex number, then z will have n distinct nth roots, which are found here. Okay, now I know that this looks super complicated, but there are 2 pieces. This one is simply in radians, whereas this one is in degrees. Okay, so don't let that freak you out. Now, if I want to find the nth root, I am going to calculate this n minus 1 times, where k starts at 0 and goes up to n minus 1. For example, if I want to find the 6th root of something, I will plug in k equals 0, 1, 2, 3, 4, and 5, because 5 is n minus 1 in this case. Okay, so it's really just applying the formula. Now, I know this looks intimidating, but I'm going to show you 2 examples of this, one in radians, one in degrees, and hopefully it will ease your fear of just looking at this. Okay, so let's take a look. In this example, it says find the 4th roots of 81. Now, if I take the 4th root of 81, I know that there are 4 results. You probably only know the real results, 3 and -3, but there are also some imaginary results that can be found by using those formulas. So, the first thing we want to do is we want to write this in polar form. Now, 81 can be written as 81 plus 0i, where 81 is A and 0 is B. Okay, but if I want to write this in polar form, because polar form is required for that formula on the previous slide, I need to find r and I need to find theta. Well, in this case, it shouldn't be too difficult. R is the square root of 81 squared, which is 81. Theta is found by taking tangent of theta divided by 0. Tangent of theta is equal to 0 divided by 81, which is 0. Tangent of theta is equal to 0 when theta is equal to 0. So, 81 plus 0i, or just 81, is equal to z is equal to 81 times cosine of 0 plus I sine of 0. Oops, 0. Okay, so this is what we are going to use. Now, using the formula from the previous slide, we end up with the following. If we want to take the 4th root, we get z equals the 4th root of 81 times cosine of 0 plus 2 pi k divided by 4 plus I sine of 0 plus 2 pi k over 4. Now, I bet that just blew your mind. So let me remind you that 0, this number here, is theta, which we found above. Okay, this number here, this denominator 4, is n. Whatever we want to find, whatever root we want to find is n. Okay, so when we evaluate this, we want to plug in values for k here and here to 3. So 0, 1, 2, and 3, because 3 is n minus 1, which is 4 minus 1 in this case. So what this means is we will have 4 answers, which are found by plugging in 0, 1, 2, and 3. I know that there are going to be 4 answers because we talked about it at the beginning of this slide. Okay, the fourth root of 81 is 3. I'm going to compute this for the 4 values of k on the next slide. So here we go. If k equals 0, I'm going to plug this in, and I have 3 times cosine of 0 plus I sine of 0. Just plugging 0 in for k. This gives me 3 times, evaluating this and this, 1 plus 0 times I, which is just 3. Okay, great. Now let's try k equals 1. Okay, if k equals 1, then I have 3 times cosine of pi over 2. Just plugging 1 in for k, plus I sine of pi over 2. Now I know that pi over 2 is here, so when I evaluate cosine and sine of pi over 2, I get 0 plus I times 1, which is 3i. Great, let's do another. K equals 2. 3 times cosine of pi. Now remember, this number is coming from the formula on the previous slide, which was 0 plus 2 pi k divided by 4. If I plug 2 in right here, I end up with 4 pi over 4, which gives me pi, plus I sine of pi. I know pi is here, so 3 times negative 1 plus I times 0 gives me negative 3. Finally, let's plug in k equals 3. So 3 times cosine of 3 pi over 2 plus I sine of 3 pi over 2. 3 pi over 2 is here. So I have 3 times 0 plus I times negative 1, giving me negative 3i. So I can conclude that the fourth roots of 81 are positive and negative 3 and positive and negative 3i. Since we're finding the fourth root, I should have 4 results. Let's try another. Okay. The good news here is that the original problem is in polar form, and we want our results in polar form. So that makes our life a lot easier. So let's just put this into the formula right away. If I want to find the cube roots, I will take the cube root of 8 times cosine of theta, which is 204 degrees, plus 360 times k, divided by n, which is 3, plus I sine of the same thing, 204 degrees plus 360k all over 3. Since we are finding the cube root, we are going to plug in 0, 1, and 2, because 2 is n minus 1, in this case 3 minus 1, which is 2. Okay, so if k is equal to 0, plugging this in, this is 2, so I have 2 times cosine of 204 degrees plus 0, because 0 times 360 is 0, divided by 3, plus I sine of 204 degrees divided by 3. This gives me 2 times cosine of 68 degrees plus I sine of 68 degrees. Since we were asked to write our results in polar form, this is one of the cube roots of 8. So this is one of our answers. I'll find the other two answers on the next slide. So if k equals 1, plugging that in, I have 2 times cosine of 204 degrees plus 360 degrees all over 3, plus I sine, same thing, 204 degrees plus 360 degrees all over 3. You can save yourself some time by writing this as r cis theta if you want. So this becomes 2 cosine of, when I divide this out, I get 188 degrees. And lastly, we will find k equals 2, which is 2 times cosine of 204 degrees plus 720. I found 720 by taking 360 times 2. So I'll divide by 3 plus I sine of the same thing. Dividing, I end up with 2 cis, if you will, 308 degrees. And those are your 3 roots. This concludes section 7.3.